Hello everybody, in today's video we're going to cover capacitors and capacitance. Capacitors are two separate plates that store energy, and capacitance is what we calculate, which tells us how much charge per volt can it store. Some examples are plate capacitors, cylindrical capacitors, and spherical capacitors. We can see we have these are the formulas we're going to derive today for capacitance. They all have different values, and once you can actually solve these, you no longer have to memorize the formulas for capacitance for these specific examples. One key idea you need to understand is Gauss law. Gauss law is the flux of the electric field through any closed surface S. This is equal to the net charge enclosed by the object divided by the permittivity of free space. This is what we get for the flux through a closed surface, and we can draw a Gaussian surface within this object, which gives us the electric field times the area of its Gaussian surface is equal to the flux. In our problems where we derive the equations, we will be setting these equal to each other so that we can find the electric field. We're going to start with a two-plate capacitor. So let's first start by drawing this so we know what we're going to be looking at. We'll start right here. So imagine we have a two-plate capacitor. We're going to have one right here, one right here. Capacitors, our capacitor is going to have a charge, so we're going to have a positive Q right here and a negative Q right here. Between these two plates, we're going to have a space D, and we know that there's going to be an electric field from the positive to the negative that we're going to use to help us find our capacitance. If we go back to our formula, capacitance is equal to the Q value divided by the voltage, but the problem is we don't know the voltage in this example, so we're going to have to use the idea of Gauss law and a Gaussian surface. Planes are the example. So we're going to have our electric field of our Gaussian surface, and then it's going to be equal to the Q inside divided by the QE, which is our space constant, which is the space constant is defined by the insulating material between the two plates. In this example, it's going to be just a space, like absolutely nothing, which makes it a constant in this example. We're going to start by finding the electric field. So the electric field is going to be equal to the Q divided by the area times our space constant. We know the area as base times height over plate. Space constant is just constant, and we have Q. Now we can solve for voltage. Voltage is equal to the integral from whatever point A to point B, we'll add over here, times the electric field, and then multiplied by d of d. In the next example, d of d. Probably better to make that dvex, but whatever. And we know that we can just pull out the E in this example because the electric field is a constant between the two plates. This is something we'll see in this example. So if that's the case, d of d is just equal to d when you take the integral. So it's going to be electric field times P. Imagine A is 0. This is our starting point. And now that we have this, we can now solve for our capacitance. But let's first substitute our electric field. We know it's going to be Q times D divided by the area times our space constant. And once we substitute our voltage in, we're going to get something like this. And then our final answer is going to be in the center. So capacitance is equal to the area of the capacitor times our space constant divided by the distance between the two plates. And this tells us a lot of what we're looking for, because capacitance is how many charges can our capacitor store. And we know that, and from this what we're looking at, we can increase it by either increasing the area or putting an insulating material that has a higher space coefficient, or we can decrease the distance between our two plates to increase our capacitance. This is how we're going to find it. Alright, now we're given a practice problem to test what we learned. So we're given a empty plate capacitor, which means we're just going to have an air between there, which is a vacuum, which is going to be our space constant. In that case, separated by a distance d, and it gives us that each plate capacitor, it has an area of 1 meter squared and is separated by 1 times 10 to the negative 3 meters for our d value. And it asks us, what is the capacitance? If you look from before, we calculated our capacitance as A times our space constant divided by the distance. If we plug those in, and let's do this right now so you guys know the values. 10 to the negative 12, and I'm pretty sure this is farads per meters, divided up right by our distance, 1 times 10 to the negative 3 meters. This will give us a value that's around 8.86 times 10 to the negative 9th power of capacitance, which is farads, which is the unit we're using. And that's part A completed right there. Now it asks us for the next part, how much charge is stored in a capacitor if 3 times 10 to the 3rd power of voltage is applied to it. If you remember, capacitance is equal to the charge divided by the voltage. All we have to do is rearrange these, so capacitance times voltage is equal to our Q value. If we plug that in, we should get a value what we're looking for, and this will tell us how much charge does each capacitor have. I mean, yeah, the capacitor. And we'll see right here, and this will give us a charge that's around 2.658 times 10 to the negative 5 coulombs. So you can see there's not a lot. This is like, each coulomb is quite a bit, if I recall, because 1 electron is equal to 1.602 times 10 to the negative 90th power coulomb. So we're gonna have a lot of electrons inside there, and that covers our practice problem. Alright, now we're going to be solving for the capacitance of a cylindrical capacitor. So let's start by drawing our cylindrical capacitor so we can get an idea of what we're working with here. So we're going to have our outer shell, and then we're going to have our inner shell, and then we're going to draw all these lines to make it show us kind of 3D here. And in our cylindrical capacitor, we're going to know one's going to be positive and the other one's going to be negative, so that there's a potential difference between the two. And we're going to be having like a Gaussian surface go around here. So what's inside here? This is where the electric field times the force is going to come from. And a cylinder is one of the Gaussian surfaces that we're working with. We know that when our object is the same as the Gaussian surface, we can just set the electric field times the area is equal to the charge inside the cylinder divided by the space constant. And we know the area. This is something you're gonna have to know on like a test for this. If you're studying for a test on this topic, no, you can find the area just by looking at the shape itself. So we have this length L right here, and then we have a radius, and then we have 2 pi, which is all around the circle. So that's going to be our area. Once we have our area, it should be 2 pi RL. If you want to get your volume, all you have to do is take the antiderivative, which is going to be R squared times L. If you ever trying to figure out what the volume is on a test, you can find the area by looking at the object and taking the antiderivative. So now we're going to set E's electric field is equal to it's going to be equal to Q divided by 2 pi RL times our favorite space constant for a vacuum. Now we need to find the velocity because we're solving for capacitance, right? Which is just a charge divided by the voltage. But we need to find voltage. That's what we're looking for, so we can substitute it out. We know voltage is equal to the antiderivative of the electric field times a distance r in this example, because r is what's changing as we get from different size Gaussian surfaces inside our shape here. And we're going to be integrating from, we're going to make this inner circle R1, and then we're going to make this outer circle R2, so we can define our range that we're going to integrate from. So we're trying to find the difference between the two, which is going to be the outers between the two shells, this distance here. And after we do that, we should have our integral defined. Now let's substitute the values that we found for our electric field, which is going to be, the only variable is 1 over r. So everything else can be pulled out to the side. Q over 2 pi times length, our space constant, and we're only integrating over 1 over r dr from r1 to r2. And this one's pretty easy if you remembered. It's going to be ln is the antiderivative to that variable. So that's going to leave us with 2 pi L times our space constant times ln, and then we're going to get r1 divided by r2, because if you remembered, ln of r1 minus ln of r2 is actually just that fraction if you want to combine them. Oh, it's back. Okay, I did make a mistake here. It's actually the other way around, so it's r2 over r1, because in your integrals it's going to be the first minus the last, which is the first is the top, bottom is the last, and this will give us our voltage. Now let's substitute it out to find our capacitance. So we know Q over Q, Q's cancel, divided by 2 pi some of this value, and then we have ln of R2 divided by R2. This is going to give us a capacitance, which we're going to write over here. So our capacitance is going to equal 2 pi space constant divided by ln of R2 divided by R1. And that's our value right here. If you want to draw a graph, we'll do a graph of ln so you get an idea what we're looking for. It's an exponential graph that grows very slowly. We can see that our capacitance only increases when this value gets closer to 0 for ln, and that's what we'd want if we want. So we just have to make the difference between R2 and L1 to be as close as possible without touching, and that's how we increase the capacitance for a cylindrical capacitor. Or we can also change the space constant for an insulated material, which has a value associated with that. And now, alright, and thank you for watching for today.